Jorg and Dennis, the work we've been doing with Jorg and Dennis. And I would like to thank Teso as well as Elna for fruitful discussion. So, no, I'm sorry, now the pointer is not working anymore. Wow, now it works. Okay, so a very simple and single question as a motivation for my talk. Just I would like to know at which stage in the AA collisions are the gypsy created. And for this, I will adopt a pretty agnostic approach. I will just look at the two contenders in the field that are either transport theory or statistical hadronization model, and all kind of coalescence taken at freeze-out. And of course, the big difference between these two contenders is that they have both some late off-diagonal recombination component, but a transport theory on the top has a primordial component. And just to picture it, so this would be basically the picture in the coalescence picture where C and C bar would evolve up the freeze-out boundary, then form gypsy with a rather complete memory loss. While if I go for the transport model, then there is this primordial component that is basically able to propagate as a white object, can still be destroyed by the QGP, but that's basically it. Now, looking, for instance, at the production as a function of n part from various PT classes, then clearly transport theories has the advantage as it is able to reproduce the experimental data, while I'm not aware of such a plot for a kind of coalescence approach, at least not as for many comprehensive PT bins. So 1-0 for transport theory, first round. Now, if we go for the V2, recently we got a pretty global view from experimental data. They are now able to show us both the V2 and the V3, and for Pion, for D, for gypsy, for epsilon. That's pretty much impressive. And then if you look at the work that Alice has pursued recently, they were making some kind of reverse engineering and extracting the light quark as well as the C quark flow from gypsy and Pion. So those are the data here. And then they would recombine those individual light quark and C quarks in order to generate the D flows, both for V2 and for V3. Then, of course, you have here basically to take some parameter that is the ratio of the mass between the light quark and the D meson. But if you accept the parameter that Alice has taken, then what you see is really a pretty good comparison between the D meson that is reconstructed and the experimental data, which pleads towards the fact that all the memory is gone, and then simply coalescence approach works at the freeze-out. Now, if you look what transport theories has to say on this question, then you see that at low PT, whatever the theories you consider, you get a good agreement with the data. But for intermediate PT, then here there is a deficit in the theory. And my interpretation is that this is due to the primordial gypsy V2, which is rather small. It is just coming from path length asymmetry. And then transport theories are not able to cope with the data for this intermediate PT. Definitively one road for all. And here I didn't talk about another possible contender that was an approach more deeply, it is deeply rooted in the theory of open quantum systems and be pushed by Jean-Paul and Miguel, where you start from this open quantum system theory, and then you derive some semi-classical approximations for an evolution of the ensemble of C and C quarks. It's very nice formalism, but it isn't put really in some, let's say, numerical tool up to now. So this was the motivation. So maybe there is a need to revisit how robustly we understand the survival of the primordial component. And of course, we have learned also from the 12 of Peters that quantum information, quantum properties are quite important. So we need definitively a formalism that preserves quantum properties. Also, it is known in the community that we should rely on very good single heavy quarks, because the question of how much this heavy quarks spectrum is thermalized or not will have a definite influence on the quarkonia production. And for this, here we are in rather good hands, because we have shown over the past years that starting from EPOS HQ, then we have a good agreement as far as the D meson production is concerned, both for the array, the V2 as the V3. So the goal of this project was somehow to build a Quarkonia overlayer to EPOS HQ, just to make sure that at least the third point here is satisfied. And for this, we took inspiration from a work done by Remmler in the 80s with a nice collaborator, which was Jörg Eichelin. And the idea here is to start directly from the basic equation, which is here the probability to find a gypsy at time t that you will take as being directly the trace of this gypsy operator, here traced out with the n-body density that includes both partons as well as many C and C bar in your system. And there was already a work done by Teso, Jörg, and Elena looking at the primordial production, so just after the overlap, using this formalism. And what they found here on the right plot is that if you just look at the diagonal contribution, you get this blue, which is typically what is called the equivalent PP. However, if you take into account this off-diagonal contribution stemming from different scattering centers, then you get a next at the very early stage, starting from this formula, we get some nice features from the quantum interference. So we wanted to build upon this idea, so build on the Remmler formalism. And now the idea, of course, is that you insert the van Neumann equation here as for the evolution of the n-body density, and you try to go with it as much as you can. And this formalism, by the way, was applied in the 80s in order to predict the deuterium production in nucleus collisions. So first, a bit of formalism. In fact, in many of the codes, we have some kind of cascade approach, meaning that for many reasons, we might not be able to preserve really the proximity between the C and the C bar in phase space. You might have shocks that somehow dissociate these guys, and they're a bit spurious. So it is somehow the cascade approach. And for this reason, and especially it was the idea of Remmler, instead of applying directly the trace at a given time, you kind of circumvent this problem and you reformulate it here by using this identity. Then you start from some initial probability. So I've shown the prediction from Teso, Elena, and Jörg, and then on the top, that's very inconvenient here. On the top, basically, you have this integrate rate. So you introduce here this rate. It is basically the differential probability as a function of time that you can calculate here directly if you know this psi operator density as well as the derivative of the n-body density with time. And then the next thing that you do is that you insert the van Neumann equation in this rate, and then you start writing your Hamiltonian. And the end of the day, what you find is that due to the fact, noticeably, that the density operator for psi commutes with the internal CC bar Hamiltonian, then the rate here reduces something that is a bit simplified, because the only thing that survives in the commutators are this kind of effective potential, which describe the interactions of single individual C quarks with the rest of the environment. Nevertheless, this commutator is still quite difficult to evaluate, at least in n-body quantum theory. And the nice idea of Remmler and co-authors was to establish a correspondence between the direct space with the Wigner space, where they could, you can see here that this commutator between the potentials and the n-body density is equivalent in the Wigner space to this evolution, which is somehow here just the modification of the Wigner density after each shock in momentum space. So you're just here taking the difference between the Wigner after the modification of the trajectories. So this means that this rather complicated commutator the Wigner densities of G psi. For this, we took vacuum potential, we evaluated then the width, and we took a Gaussian approximation to make things simple. And as for the n body Wigner density, then we simply took semi-classical trajectory.
I don't hear Paul. There is some sound breaking, at least for me.
For me, it's technically very cumbersome as well. I don't know what.
Now it's okay, but there was another break before. Okay, never mind. Thank you.
I'm sorry, Anton. Maybe the connection in different places of the world. Well, I can hear myself pretty loudly. That's what I can say. I'm sorry.
Yeah, no problem. Yeah, thank you.
So this is for operational purpose. Then the rate that you get. So this kind of schematic here realization. So what you do is that you follow the trajectories of both heavy quarks and anti-heavy quarks, and then each time you have a collision here with the rest of the system, then you look at the inferred modification of the Wigner density here of your quarkonia. And then this difference somehow represent gain and loss term, but on the quantum level. And by considering all these processes, then you are able here to build the gain. And the thing that is interesting that you should notice is that we sum, in fact, on all possible Q and Q bar pairs. So if I give 10 heavy quarks and 10 anti-heavy quarks, then the rate of formation will really imply the sum on all possible combination. Another nice feature of this formalism is that from the viewpoint of heavy quarks, the only thing you need is to know the trajectories. And then this means that you can apply this overlayer to any model that you could have for the evolution of single heavy quarks. And then in the end, you reconstruct the final distribution using this formula. But however, one thing that was missing apart from this formalism is a genuine QQ bar interaction in EPOS. This we do not have. I mean, we are going precisely the cascade mode. And it turns out that implementing this QQ bar interaction is something that is very, very important in order to get reasonable prediction as compared to phenomenology. And simply also from the pure viewpoint of theory. So basically, we took one of the state-of-the-art potential obtained recently by those two gentlemen here, and then we decided to implement it numerically. Now, there's kind of little problems if you start implementing such potentials without going in the Hamilton-Jacobi coordinates, then you see that the equation of motions are simply divergent. That means that at some point, the numerically, this problem is unstable. And then it requires that you go in the Hamilton-Jacobi coordinates in order to have such stability, but this can only be achieved by going to the center of mass of the system. So you are facing a problem where you have to describe the evolution of 100 C quarks coupled with 100 anti-C quarks, and then you need to go to each local center of mass. It's a bit technically involved. At some point, what we considered was it's technically involved, and also there are little discrepancies each time that you move forth and back here to the center of mass frame. You are introducing here some small glitches with respect to your main evolution, which is done in the lab frame. And this is why if you go at a large PT, these little glitches here will be seen as some numerical noise and are disturbing the algorithm. So it's still an open problem. At some point, we considered going with some retarded forces, but there are other problems if you consider retarded force. And one of these problems is, for instance, that energy is not conserved. We can discuss about this if you wish. But in the end, nevertheless, so going by this center of mass strategy, what we could look at was the number of C and C bar that stay close together in time as a function of time for 3 cases, both taking no CC bar interaction. That is really here the curves are the lowest. So basically nothing is preserved at the end. Then this is what happens if you take the screen potential of Lafferty and Rodkoff. And this is what you would get if you would take the vacuum inside the QGP. And then you can also see on this plot the effect of so we have these CC bar states that are surviving over time. Now you can also look at the consequences of the CC bar trajectories. So you can look what you have. For instance, if you turn on the interaction with the medium, and then basically you compare this set of 2 curves with a set of 2 curves, and then what you can see, the effect of the medium is simply to give you some energy loss, and then the distribution of those pairs that are close together in total PT get shifted from 3 to basically 1.5 GeV. And on the top, you can also see that if you look at the potential effect now, it really helps you, as already shown, to populate these close CC bar pairs. And this is true for basically all PT. Last term in models they have not discussed that somehow in this internal Hamiltonian, of course, what we would like to put is precisely this temperature-dependent potential, meaning if we go back to the formalism, that the only way to guarantee that this commutator is still 0 is to work in the local basis, and meaning that psi will be now considered as a local state of the temperature-dependent potential. And the price you have to pay, and then if you come back to the rate and take the time derivative of the definition, then you get a new term here that has to do with the derivative of this gypsy basis with respect to time. So this is what we call the so-called local rate that you have to put on the top. Basically of this genuine Reimer term. So with this, I am set basically, and I will now show some results of this approach. First, looking at the initial production. So of course, this projection here can, sorry, I was too fast. This can only be done, of course, once the temperature, or there is a misprint here, once the temperature is lower than the dissociation temperature. It is taken as 0.4 GeV in this approach. Otherwise, simply the local state does not exist, and then we form nothing. So now when we look at this primordial, this initial production, of course, the initial time at which the temperature locally goes under the dissociation temperature is distributed. Okay, it's not instantaneous. And this is why, if you consider here the number of gypsies that are initially created between time t and time t plus dt, where dt is 0.25 Fermi over c, you see, for instance, here in central collisions, this initial production is really delayed with time. And this is due to the fact that locally, at some places, we haven't reached a temperature that is lower than the dissociation temperature. Now we can also look at absolute numbers, and what you see if you look at the ratio of those primordial gypsy, so that are early formed with respect to the total number of CC bar pairs, in fact, they do not scale, and contrarily to what Tessot, Elena, and Jorg have found, in fact, in a more central collision, this ratio is even decreasing. And the reason is simply because we are not considering the same basis. We are considering a basis that is local in temperature. In order to better understand this phenomena, what we did is that we rescaled this primordial production by the square of the number of C quarks. And here, clearly, you can see that indeed, at initial times, we have this effect of temperature depletion, why later on we get here roughly the same production, and we get even after rescaling even a bit more production in the central collision. So now I go directly to the total production over time. And here, let me differentiate two sets of curves. So the one there where the CC bar potential is turned off. So what you see is that after the local production here, what will happen is that this Remle collision term will basically destroy most of the gypsides that have been created. So we get rather little numbers at the end. While if you put this potential on, then in fact the gypside will keep on accumulating. So this correlation that we had initially will get strengthened over time. And this is due both because the collisional Remle term is reduced as compared with the pollution with potential off, but also because we have a strong increase of this local rate, and those two somehow go together for bringing you this picture. Now, let me go to other observables. This is a final gypside production as a function of PT. So here, what you should look is basically the comparison between the green dots, which represent a full model, and the black dot for Alice. And you see a pretty good agreement, which has to be taken with a grain of salt because we have no feed down from higher states right now in the model. If we look at the array, agreement is less good. And this is mainly due to the fact that the equivalent production in PP does not fit as good. So within this coalescence approach, does not fit as good in the PP. And we decided to stick to the model both for the AA and the PP. Now, looking at more data that are here, the production as a function of the number of n part, then we see a rather, well, there are still fluctuations, and here we are working at mid rapidity. I mean, we plan to do the forward rapidity in the near future, so it's not the most precise comparison, obviously, but nevertheless, for this kind of first try, we get a rather good agreement with the data. And now let me finally come to the V2 that was somehow the most difficult observables to cope with. And here we compare still because we're doing prediction at mid rapidity. So we compare with the best what Alice can offer us at mid rapidity. And then we commit the terrorist crime of comparing prediction made at mid rapidity with V2 measured at diamond arms at forward rapidity. So I hope nobody will kill me. And at least what we can conclude is that we get significant V2. And I would even say we get maybe more V2 as we should, at least as compared to theory. So experiment, sorry. And now, in the end, in order to understand where the excess come from, let me break down the production between two components. There's the diagonal one and the off diagonal. So what I call diagonal corresponds to the C and C bars that were formed in the same nucleon collision. This is what is called primordial in other approaches. And then if you look at the decomposition of array as a function of off diagonal and diagonal, there is nothing too much surprising. Okay, you see that at low PT, it is indeed the off diagonal that dominates. Okay, the kind of strongly diminished at a large PT. C and C bar, which were not correlated initially, they have difficulties to find themselves at large PT, while the diagonal component here becomes larger simply because the energy loss acting on this diagonal component is smaller and smaller proportionally to the energy itself. And if you look now at the decomposition of the V2, what we observe, okay, and is really different with respect to the other transport approach, is a rather significant component contribution from the diagonal component here. And this is what helps to get a significant V2 at intermediate peak. Now, finally, before concluding, what is the physical picture behind this? Well, we know that when we have to consider here the interaction of some QQ bar with the QGP, what people usually consider is the relative distance between the C and the C bar is so small that this is completely white and then does not interact with the medium. And this is true, strictly speaking, when the relative distance is smaller than the correlation length in the Gluon fields, which is of the order of 1 of the temperature. So it means that indeed for temperature that is small with respect to alpha S MC, this object should be considered as white. But this criteria is not met for all the temperatures present in the QGP. And for some of the temperature, and in particular for the early and intermediate stage, we might well be in the other regime where in fact the interaction between external patterns and both Q and Q bar should be considered as the sum of both individual interaction here that are completely uncorrelated. It is exactly what we have in a model. So one might dispute whether it's a good or bad approximation to consider this all over the place, but it is definitely what we have done. And in this respect, it allows somehow to offer a different perspective as with respect to the traditional approaches in transport theories. And now let me come to my conclusion. That will be simply the answer to my original question. At what stage of the AA collisions are the gypsi created? So the answer for me is in this plot. And the answer is that correlations are built continuously as soon as the temperature is smaller than the dissociation temperature. And these correlations are strengthened with a cooling temperature. So definitely, we do not see some kind of sharp rise of gypsi production at the later stage. And I don't know how much I'm doing with my time. Well, I'm at the end, basically. So, of course, obviously, some perspectives. So in the short term, we need to include the higher states feed down and plus the shadowing. We need also to include this model in EPOS 4, what will give us then access at Rick physics. Then, of course, one strong science driver here in the field is the BC. So we definitely want to investigate the BC production here, and midterm means before quark matter, and then basically in the long term, what we'd like to implement a better color dynamics and taken into account the effect of QQ bar distance on the interaction between the QQ bar precisely and the QGP constituents. Okay, thanks a lot.
Thank you very much. So let's start with a question in our audience, and for Zoom participants, please raise your hand if you wanted to ask questions. So, okay, Taiso. So just speak.
Thank you for the nice talk. You included the heavy core potential, but the heavy core pair could be color octet and color singlet. Yeah. Did you separate them?
Yeah, yes, quite good question. So here, as I said, really including genuine color dynamics for this n-body physics would be the next stage. So here, the assumption that we make is that rather early pairs are kind of separated between those which are singlet, and then they are considered as being singlet all along the evolution, and those which are octet, and then pairs which are octet definitively do not contribute to this gypsy production. So it is basically a crude way to deal with the color dynamics, but in order to do better, then what we need to do is to introduce those transition operators between singlet and octet. And this is what we plan to do in the future.
Okay, thank you. Some other questions from our audience? I don't see some hands. So we have few questions from Zoom participants, and I see 2 hands. I don't know who was the first. Okay, Anton, please go ahead.
Thank you, Paul, for the nice talk. I have a comment and a question. The comment is about your first scoring 1-0. Well, yes, you can score it like this, but the truth is that we didn't find time to do these predictions. It's not that we cannot.
Operationally speaking, then it is 1-0.
Yes, it's 1-0. It's okay, but you know, it's an technical 1-0.
No, but let us be more serious, Anton. I mean, here the fact is not only that. You see, we know. Okay, here I'm just looking at this, but we know from the spectra that the gypsy spectra that we find are kind of algebraic line. Okay, they will never be able to fit by something that is of a thermal behavior.
Sure.
But okay, it's 1-0. If you do the job, then it was just a motivation.
Yeah, no, don't worry. high PT part, we anyway have not much to say about. So in any case, we restrict ourselves to the 5 GeV region, right? But my question was, you were only talking about J-psi, but how do you treat D mesons? I mean, is it just enough to look at the CC bar and ignore the rest, or maybe you don't?
I'm sorry. No, I'm sorry. I was too fast, definitely. My point is the following. Okay, we are building just another layer. Okay, to EPOS HQ, and so it is the things that has been presented over the years. This EPOS HQ is a thing where we had pretty good, let's say, comparison. So the D mesons are still the same. Basically, we do not touch the D meson at all.
Thank you. So there is competition, and yes, everything goes. And there is also the canonical effect, I assume, for the open charm and so on. This is, I assume, all okay. Yeah, thank you.
No. The things that we do not do here, indeed, we are not working in canonical. Once a C quark, because we are dealing with this many CC bars. So once a C quark contribute, we are really calculating the probability to form a J-psi, but we do not have a Monte Carlo evolution. So we do not decide at some point that one precise CC bar will be converted to a J-psi, and then those CC bar are kind of removed from the rest of the world. It's really computationally a probability, a rate, but the C quarks are still there.
Yeah, okay, but this is not a big deal since J-psi is so little compared to the open charm. I think that's all fine. Yeah,
that's the point. Yes.
Okay, now we come to question from Ralph.
Hi, Paul. Very nice and interesting talk and good results. I just wanted to make one comment and one question then. So this V2 picture that you showed in the beginning, I think an important piece of information in there is that the way, and you may blame us for that, and that's fine. The way the PT dependence of the regeneration is modeled here is with the blast wave. So it and that's why we, at the end of the day, miss out on an intermediate PT region that is also apparent from the RAA, where there's a dip in our calculations relative to the data. So just for clarification, so what we think really is going on there is that this non-thermalized charm core coalescence is very important there, and that's also, I think, what you find, and that's good. I think it's very nice. I have one question, one simple question for the time being. So if one does these quantum approaches, it's of course important to check the quantum physics involved, but I think it would also be important to check in how far the semi-classical approach actually captures the main features, right? And in fact, in the first paper by Gossiaux that you quoted, they made the explicit statement that a rate equation approach gives an excellent representation of the average quantum approach. So can you comment on that?
Yes, Ralph. I mean, this point is very well taken. In fact, in another word that we are doing with Stéphane Delorme, and you can find the presentation on this strong conference that took place two weeks ago. Then we are basically solving the quantum master equation, and we are presently investigating the validity of the semi-classical approach. Because in the end, both in this work that we have presented here, we are also confronted to this semi-classical approximation. And for me, it's still a question, a burning question, whether to know whether it is a good approximation or not. So presently, I cannot really have a definite answer to this. We did the best what we could in the semi-classical evolution. While, of course, if you're considering single pair, then of course it's possible to preserve the full quantum. I mean, it was Peter has shown, but we want to go for the CC bar.
Okay, please, very short question from Minher and short answer.
No.
Yes, Paul, thanks for your nice talk. So you emphasized the role of the deflection for the primordial J-psi, but how are the single heavy quarks interacting with the medium in your formalism?
Well, these are exactly the same interaction as what we have published with Monte Carlo plus F+2. All of these reports, these comparisons of which you are also co-authors, it's exactly the same model. We did not touch a single line for the heavy quarks evolution. It's just done with pure elastic. I mean, we don't use radiative here. It's more the elastic that we are using.
Okay, I think we have to thank Paul again.